I see a product of two functions and then minus and just x to the third and a function on the other side. So the first function prime is 1 times the second function plus the first times the second function prime. Cosine prime, sine prime is cosine y times the inner function prime this. Then I have negative 3x squared, which is just plain x. And then I have dy over dx. Is this step clear? Everyone? Is that a yes?
Why is it x times cosine y? Is that the first function times?
So 1 times 2 prime is 1 prime times 2 plus 1 times 2 prime.
Okay.
1 prime is 1, 2 is here, and then plus, and then the first function is here. And all this is the second function prime.
Okay.
And then minus 3x squared equals dy over dx. Is this okay? Yes, Diwa?
I thought the derivative of sine y cos y, dy.
The derivative of sine x is cosine x. The derivative of sine of a function is cosine of the function times the function prime. Good. So then I will move this term to the other side because it has the dy over dx. So sine y minus 3x squared equals 1 minus x cosine y dy over dx. So the left-hand side is just this term and this term because they don't have dy over dx. This goes to the other side because it becomes negative. And I factor out dy over dx from these two terms. So finally, dy over dx must be a fraction. This at the top and this in the denominator. Anything else? Anything else? Thank you. Thank you. Great. I see it already. You want to copy it? That's fine. Yeah. Okay. That's fine. So let's look at the other one. That's fine. That's okay. That's okay. Good. So let's look at the yellow form. The yellow form, we differentiate both sides. We have 2x minus. This is the product rule. Be very careful. Put it in brackets. Leave the negative 1 outside. X cubed prime is 3x squared times y squared plus x cubed times 2 times y times dy over dx equals 3. Is this clear? All steps? Yes? So then 2x minus 3x squared y squared minus 2x cubed y dy over dx equals 3. I will move this term to this side and I will move 3 to this side. So then 2x minus 3x squared y squared minus 3 equals 2x cubed y dy over dx. So dy over dx is this. Any questions on this? Any questions on this? Yes, Ricky, go ahead. So this is a product of x cubed y squared. This is the first function. This is the second function. So I left a negative outside. I differentiated x cubed to get 3x squared. I multiply by the second function and then plus. I copy the first function. and multiply by y squared prime. We just did that with Braden asked for that a few minutes ago. So 2y times dy over dx, and the right-hand side is 3. Better? Very good. Okay. Any questions? Yes.
Where does the 3x squared y squared come from?
The first function prime is 3x squared y. The first function prime is 3x squared times the second function plus the first function times the second function prime. So this is 1 prime. This is 2. This is 1. And this, including the y dx, is y2, second function prime. Y prime times 2 plus 1. 1 prime times 2 plus 1 times 2 prime on this product. So 3x squared times y squared plus x cubed times 2y dy dx is the product rule applied on x cubed y squared. Yes, Vanessa?
3x prime is 3.
X squared.
No, I'm telling you something different. So the other side of the equation, that, yeah, 3x.
Yes. What is the derivative of a constant times a function? Is the constant times the function prime. X prime is 1. So that's why the constant is 3. Good. Let's wrap up section 3.5, which is differentiation, implicit differentiation. But not before we talk about just 3 inverse trig functions. Inverse trig functions. There are 6 inverse trig functions. However, I'm only going to ask you to look at 3, just 3 inverse functions. For f of x equals sine x, what is the inverse function of sine x? Is denoted by f to negative 1, f inverse. We shouldn't say f to negative 1. It's f inverse. That's the notation. It's sine inverse, which does not mean 1 over sine x. It does not. Or arc sine x. So just to make sure, in the graphing calculator, I need to say this because I've seen it in your work sometimes. So sin is this, sine. If the mode is in radians, then I'm going to put sine, for example, sine pi over 2. What is sine pi over 2? What does sine pi over 2 equal to?
1.
Excellent. Okay? But now if I want the inverse function is right here, the same key but in blue in the software. Second, this is sine inverse. And if I put 1, because I'm applying it from the other side, right? Sine of pi over 2 is 1. Sine inverse of 1 should be, let's see what we get. I'm just curious. Of course, the calculator will not present pi over 2. It will present pi 3.14 divided by 2. Okay? So this is not 1 over sine, but the inverse function of sine. Okay, good. The other 2 functions that I would like us to remember are, of course, f of x equals cosine x and its inverse, cosine inverse, or arc cosine x. Please remember they are the same thing and we use them interchangeably. When we will use this? When I'm lazy and it's difficult for me to type the power. It's the same thing. Of course, if I type this, I have to type a power. If I type arc cosine, I don't have to type a power. It doesn't matter, of course. We are using both. And the last one is f of x equals tangent x. And we know this graph already by heart of which function, what function I'm referring to, which function I'm... Exactly. Or tangent inverse or arc tangent. We looked at this graph so many times because you will see it's so important in the long run. So this is the graph of arc tangent. Okay, so what do I want with this? I want their derivatives. Just these three functions. So sine inverse x prime, we're not bringing down the power and subtract 1 from the power. Careful, this is just a notation, is the inverse function of sine prime, is 1 over the square root of 1 minus x squared. Like with the rest of the functions that we said they are so important, please remember this one. So we are adding this to the list of what is the square root of x prime?
1 over 2x.
Very good. What is 1 over x prime? Very important to remember, if you can. You change it into x to negative 1, and that's what you get. Okay, cosine inverse x is the exact same thing, but with minus in front. And the last one, which is tangent inverse, very important function. Tangent inverse x prime, very nice. So these are very important. Let's practice this and move on to 3.6 and finish that up. Okay, on page, you have the other formulas in the book. I don't care for them, and I will not test you for the rest. You can always find them in the book or use the formula. If I put something like this, the formula will be given to you, but I'm only testing you on basic things that you will remember in the long run, not on some definition. Okay. Or formula that you may or may not see again. Let's say on page 216, you can choose if you'd like.
Is this 3.6?
Yes.
Okay.
No, this is still 3.5.
Okay.
Still 3.5. And then we have to practice 3.6. Okay, I'm going to choose 54. And then you can choose another. Y equals tangent inverse, and that is applied to x minus the square root of 1 plus x squared. Of course, we are asked to find y prime. In this case, there is no need to write dy over dx because we're not differentiating implicitly. So how do I start? What is the starting point? What do I need to do? So I'm differentiating tangent inverse, which is 1 over 1 plus all this squared. Times all this prime. The first function prime is 1 minus. I reached this section where, or the radical, where I have to differentiate a radical. That's why I refreshed your memory on how to differentiate a square root. But this is of a function, not plain x. What do I write? How do I differentiate the square root? 1 over, okay, one more time. When we differentiate a square root, we have 1 over 2 times the square root of that expression times the function prime. Okay, so 1 over 2, the square root of 1 plus x squared, times the inner function prime. How much is the inner function prime?
2x.
Very good. 2x at the top. We can clean it up a little bit by simply simplifying 2 with 2, finding the least common denominator here, and what do we get? It is possible, I have no idea, that if we square this and try to simplify further, it may be further simplifiable. What is the least common denominator here?
1 for x.
There is only one, right? The square root of 1 plus x squared. So then the square root of 1 plus x squared minus x. So if you'd like, as an extra credit, if you'd like to try to see what that is when you square it and add 1 and see if you can further simplify it. If not, this is good enough. So please choose another with inverse functions, inverse trig functions. So then we can move on. Would you like to choose, or I will?
Wait, so is that the final answer?
If you square this and you add 1, you may be able to simplify something. I don't know. So for now, I'm going to leave it as is. And if you'd like to further try to simplify it, or we can after class. I don't want to spend too much time on simplifying this one. But we can do it after class. Or you can do it for some extra credit. And let me know what you get. Okay, would you like to choose another, or I will? Yes? Okay, 58 caught my eye. So in 58, we'd have y equals cosine inverse of sine inverse t. So let's analyze this first and see what we have. So we have a plane inverse function sine, which is okay. But this one is inside the inverse of cosine. So obviously the chain rule applies here. This is the outer, this is the inner. And this is just plane. So outer, inner. So ready to differentiate? So y prime equals yes, -1 over the square root of 1 minus, and I have to square this. Do not say that the power will be -2, careful. So this is sine inverse t that has to be squared times the inner function prime, which is 1 over square root 1 minus t squared. And there is nothing we can do here. Any questions? Any questions? Okay, let's go back to logarithmic differentiation and finish 3.6. So back to log differentiation. One more time, let me just refresh your memory. One application of this is when we have a function, you can say this is a function as well. How come that you don't use logarithmic differentiation on this? Because I don't need to. I have a formula for this. It's e to u times u prime. But any other function, like, let's say, x squared plus 3x plus 2 raised to 2x minus 1. There is no formula for this. So this is our y. So if we denote this by y, then there is no formula for differentiating something like this. That's our question. What we have to do is to both sides of this equation, we apply natural log. Natural log on the left-hand side equals natural log on the other side. Let's write it as x squared plus 3x plus 1 raised to 2x minus 1. And now be very careful when you bring the power in front, you have to put parentheses. So one more step, 2x minus 1 in parentheses, natural log of x squared plus 3x plus 1. And now we will differentiate implicitly. So as you see, logarithmic differentiation doesn't do the job alone without implicit differentiation. So last time, I added in one more formula, one more differentiation rule, if you want, as natural log of x prime is 1 over x. Of course, natural log of a function, u of x. Can anyone give us this formula? I didn't finish this. I'm just refreshing your memory on the two rules. What will this be?
1 over u of x.
Exactly.
Times u of x or something.
Exactly. Excellent. Well done. So now when I differentiate natural log y, remember y is a function of x. So it's this formula or rule. So it's 1 over y times dy over dx equals. Remember now, this is a product. We have two functions here. Always establish what you have to differentiate. So this is a product of two functions. Furthermore, this is a function inside natural log. So not only the product rule applies here, but also the chain rule for natural log. So let's differentiate together. The first function prime is 2 times natural log x squared plus 3x plus 1. Plus, remember the product rule has to have a plus somewhere. Plus what?
Plus 2x.
2x minus 1 times, now we differentiate the natural log, which is 1 over, it's this formula, x squared plus 3x plus 1 times the inner function prime, which is plus 3. If you write it like this without parentheses, that would be wrong. Now, one remark I have about your homework that I just returned today, please do not multiply the factors in the denominator. It's a waste of time. It's not wrong, but there is no ever need to multiply the factors in the denominator. Unless, for example, here, I don't know, maybe I have to multiply these two to simplify. Who knows? That's possible. But other than that, if you have just plain factors, do not multiply them. It's a waste of time. Okay, so remember we are after this. So then I have dy over dx, and I will have to multiply both sides by y. But what is y? Y is the entire function. So I will write x squared plus 3x plus 2, everything raised to 2x minus 1. And open a bracket and see if we can do anything here. Not that much. 2 natural log of x squared plus 3x. Somehow I wrote 2 here, but then 1. Sorry about that. I don't know. My 2 changed into 1, and no one said anything. No, it's not your fault. Okay. Of course, it's my fault. My apologies. Plus, I will multiply these two, because even if I factor this into x plus 1 and x plus 2, I will not be able to simplify. So I will multiply these two at the top. But there is nothing else we can do. So this will be 4x squared, and then that's minus 2x and plus 6x. So that's plus 4x and minus 3. And this is it. So we used logarithmic differentiation. We applied log, and then we used implicit differentiation to find the derivative of this function. So the derivative of that function is the function itself times the brackets. Please, Tiwa.
How did you get the 4x squared plus 4?
2x times 2x is 4x squared. 2x times 3 is 6x. And minus 2x is 4x. And negative 1 times 3 is negative 3. Just to use FOIL on the side for these two. Good. Would you like to choose another example? Please do. On page 223. Anything you like. From 39 through 50. And then I would like to draw your attention on something before we move on. So do I get to pick, or you want to pick? Anyone? Because I think we need to practice at least one more. Would you agree?
Yes.
Okay, so I'll ask you, which one would you prefer? So sine raised to natural log raised to cosine, y equals the square root of x, everything raised to the x power, anything else? Any function that we use logarithmic differentiation on?
39.
39. Very good. 39. The first one? Okay, fine. So for 39, we have y equals x squared plus 2 squared, and multiplied by x to the fourth plus 4 Everything to the fourth power. This particular example does not need logarithmic differentiation. In this particular example, I can use the product rule and the chain rule. However, there is another way which you may enjoy by applying natural log first, which makes no difference. Okay, ready? So when we apply natural log to the left-hand side, then we apply natural log to a product. Anyone remembers? So natural log applied to this side, natural log applied to that side. Anyone remembers what is the rule for log applied to a product? Okay, let me refresh your memory. Log applied to x times y is log x plus log y in any base. If it's base e, it's natural log. If it's base 5, it's natural log base 5. So when I apply natural log to this product, I will say natural log of the first plus natural log of the second, because it's a product. So natural log of x squared plus 2 squared plus natural log x to the fourth plus 4 to the fourth. Please do not say that we distributed natural log to something, because that's not a distributive law. We are using the property of logs that says whenever we apply log to a product, we can split it up into a sum of 2 logs. Okay. Now, of course, we have the property that we used so many times already. The power goes in front as a factor. So then natural log y equals 2 natural log x squared plus 2 plus 4 natural log x to the fourth plus 4. And you can say so many steps, a lot of preparation. You haven't even started to differentiate. I will right now. Yes, Vanessa?
Do you need to add like the exponent that's the last part since you moved the fourth right now?
There is no rule for log of a sum.
Okay.
So we have 3 rules. Log applied to a product, log applied to a ratio, which makes this a difference, and log applied to a power. No one can simplify log applied to a sum or log applied to a difference. That is carved in stone. Very good question. Thank you. Okay. So now we finally differentiate the left-hand side and the right-hand side. This was all prep. 1 divided by y times dy over dx equals 2. 1 over x squared plus 2 times 2x, right? Right? So 2 stays outside. When I differentiate log of a function, 1 over the function times the inner function prime. Are you with me, everyone? Yes, Vanessa?
I don't understand why it's a fraction.
Okay,
Why it's under 1.
very good. Natural log of u of x prime is 1 over u of x times u prime.
Okay.
Then plus 4, 1 over x to the fourth plus 4 times the inner function prime, 4x to the third. So finally, dy over dx, I have to multiply by y, both sides by y, to just solve for dy over dx. But y is all this. That's our y. I'm going to copy it. X squared plus 2 squared, x to the fourth plus 4 to the fourth. And now 4x over x squared plus 2 plus 16x cubed over x to the fourth plus 4. You will get this exact same thing if you use the product rule. I would recommend finding the least common denominator and simplifying.
Can you explain that last step again? Dy dx.
Yes, so if I have 1/2 x and I'm solving for x, I have to multiply both sides by 2. But I have 1 over y.
So multiply by 1.
I multiply both sides by y to get just dy over dx on the left-hand side. But y is all this. Better?
Yeah.
Okay, so I recommend not leave it like that, but finding the least common denominator. Any questions? Yes, Nathan, you may see something that I don't. Nathan, Jared, any questions? Okay, Vanessa?
I don't know how you got that with the brackets.
2 times 2x, 4x. 4 times 4x cubed, 16x cubed.
Okay.
And I just copy the denominators.
Okay.
But now I want to write x squared plus 2 squared, x to the 4th plus 4 to the 4th, and find the least common denominator, which is obviously the product of the two. The first top needs an x to the 4th plus 4, and the second top needs an x squared plus 2. Why do I do this? Here's why. That's the reason why I do it. That's why we should not stop here. What I would say, well, I'm going to finish in a minute, but what I would say is applying logarithmic differentiation on this problem is like something like doing this instead of this. I think it's way more work. Maybe, and also the prep instead of applying the product rule. But it's good to see an example like this, just in case. At some point in time, you may consider it. But I think it's way longer. Why I think it's longer? Because, first of all, look, I have to go through all this prep before I even differentiate. Then I differentiate implicitly. Then I multiply by y, which is this function. And then I realize, okay, I can further simplify it. So what we have at the top, we get 4x multiplied by these two, and 16x cubed multiplied by these two. To tell the truth, what I would have done, I would have factored out 4x from the beginning and not have to worry about multiplying so much. So this would have been 1, and this would have been 4x squared. But, okay, I didn't do it, so let's continue as is. So this is 4x to the 5th plus 16x plus 16x to the 5th plus 32x cubed. I ran out of room like always. So this is x squared plus 2 to the first power, x to the 4th plus 4 to the 3rd power. And yes, I would say the same thing. 20x to the 5th plus 32x cubed plus 16x. And I will factor out a 4x. 4x outside, x squared plus 2, x to the 4th plus 4 to the 3rd. And we have 5, x to the 4th plus 8x squared plus 4. In my opinion, way more work. Okay, I'm checking my terms. That's 20, that's correct. 32, I think it's correct. 16. Factor of 4x, I have a 5x to the 4th. I have an 8x squared and a 4. Which I think would be easier if we would just use the product rule. Okay, so let's do still one more and then we move on.
I'm still copying.
Yes, I am waiting.